On the evening of July 31st, 2026, at 7:46 p.m. local time, the ground west of Naples let go with a magnitude 4.7 earthquake, the strongest tremor recorded in this part of Italy in 40 years. Buildings cracked in Pozzuoli. Falling debris injured more than 24 people, 2 of them critically. Rail lines across the Naples network shut down within minutes. The port of Pozzuoli closed entirely, cutting off ferry service to the islands of Procida and Ischia in the middle of peak summer tourist season. Aftershocks kept coming through the night, more than 60 of them by the time the sun came up, and residents across Pozzuoli, Boccoli, and the Neapolitan districts of Bagnoli, Agnano, and Fuorigrotta were left standing outside their homes at midnight, waiting to see if the ground would move again. It did. This is not an isolated event, and it is not the first time this year that a shaking night has sent hundreds of thousands of people out into the streets. It is the latest, sharpest data point in a story that has been building underground for more than 2 decades, and scientists studying it are now saying something they were far more cautious about even a year or 2 ago. The system beneath one of the most densely populated volcanic regions on the planet is accelerating, and the acceleration itself appears to be self-feeding. Today, we are going to walk through exactly what is happening underneath Naples, why the ground keeps rising, what magmatic fluids actually have to do with all of this, and what a peer-reviewed study published earlier this year says about where this trajectory could be heading by the early 2030s. No dramatizing, no doomsday framing, just the science as it currently stands, because the actual picture here is unsettling enough without any embellishment. The feature we are talking about is called Campi Flegrei, which translates roughly to burning fields, and it sits just west of Naples, partly on land and partly submerged beneath the Gulf of Pozzuoli. Unlike Vesuvius, the volcano most people picture when they think of danger near Naples, Campi Flegrei is not a single cone rising dramatically out of the landscape. It is a caldera, a vast collapsed depression roughly 12 kilometers across, formed by 2 of the most violent eruptions in the region's geological history, one dating back around 39,000 years and another around 15,000 years ago. Within that sunken landscape sit more than 20 separate craters and volcanic vents, including the sulfur-streaked Solfatara crater, whose steaming vents and bubbling mud pools have drawn curious visitors for centuries, without most of them fully grasping what they were actually standing on top of. Roughly 500,000 people live directly inside the caldera itself, and the wider Naples metropolitan area, which sits immediately adjacent to it, holds close to 3 million more. There is genuinely no other comparably dangerous volcanic system on Earth, with this many people living, working, and raising families directly inside its boundary. What makes Campi Flegrei unlike almost any other volcano you have probably heard of is a phenomenon called bradyseism, a term borrowed from Greek meaning slow movement. Instead of building toward eruption the way most volcanoes do, with a relatively narrow window of escalating signs before an event, Campi Flegrei's ground surface rises and falls over years, sometimes decades, in response to pressure changes in the hydrothermal and magmatic systems churning beneath it. This is not a subtle effect you would need instruments to detect. The clearest physical proof of it stands right on Pozzuoli's waterfront, at the ruins of what is known as the Temple of Serapis, actually the remains of a Roman-era marketplace. 3 surviving marble columns there are marked with distinct bands bored into the stone by a specific species of marine mollusk, clear physical evidence that those columns spent a long stretch of history sitting below sea level before the ground beneath them rose again. That single archaeological detail, columns drilled by sea creatures now standing well above the waterline, is a 2,000-year-old record of exactly the kind of ground movement scientists are now measuring in real time, with satellites and precision instruments. The current episode of unrest is not new. It began back in 2005 when instruments first started picking up shifts in gas emissions, a rise in the frequency of small earthquakes, and the beginning of a sustained uplift trend in the ground around Pozzuoli. For years, that uplift crept along slowly enough that it barely made headlines outside of specialist volcanology circles. But the trend never reversed, and it never stayed flat. Instead, it has done something scientists specifically flag as a warning sign in any complex physical system. It has accelerated, and the rate of that acceleration has itself been increasing. By November of 2024, the total accumulated uplift in Pozzuoli had reached 1.33 meters since the unrest began. By the end of March this year, that figure had climbed to roughly 1.63 meters, meaning the ground has now risen more than a full 1.5 meters since 2005, with about 25.5 centimeters of that rise arriving just since the start of 2025 alone. Read that again, 1/4 meter of new uplift in a little over a year, on top of ground that had already risen more than a meter over the 2 decades before that. This is exactly the kind of pattern that shows up when you plot the data on a graph, and the curve stops looking like a gentle slope and starts bending upward into something closer to a hook. Ground uplift on its own would already be a significant scientific story, but it has not been arriving in isolation. It has been accompanied by a steadily climbing rate of seismicity, and the earthquake record over the past year and a half reads almost like an escalating drumbeat. In October of last year, a swarm of more than 40 earthquakes struck in a single night, rattling residents awake and sending a fresh wave of anxiety through communities that were already living on edge. By February of this year, that number had climbed further, with INGV, Italy's National Institute of Geophysics and Volcanology, recording approximately 70 earthquakes in a single week between February 23rd and March 1st, with magnitudes reaching as high as 3, 5, and the majority of the activity concentrated directly beneath the Pozzuoli-Agnano area. The following week brought 47 more, a slight easing that offered a brief moment of relief before activity picked back up again. Then in April, a swarm of 16 quakes, the strongest measuring 3. 3 woke close to 200,000 residents in the early hours of the morning, with the epicenter located in the stretch between the Solfatara crater and Mount Olibano along the Naples seafront. In May, a shallow magnitude, 4. Earthquakes struck at just before 4 in the morning local time, triggering a swarm of 12 additional quakes concentrated offshore between the Pozzuoli and Boccoli sectors of the caldera, strong enough that local authorities ordered precautionary school closures in the Bagnoli Fuorigrata district, while engineers inspected public and private buildings for structural damage. And then came July 31st, the magnitude 4, 7 event that surpassed everything before it, officially the strongest tremor recorded in this specific phase of unrest, surpassing 2 separate magnitude 4. 6 events that had occurred the previous year and briefly held the record themselves. Notice the pattern in that sequence. It is not simply that earthquakes keep happening at Campi Flegrei, which on its own would not necessarily be alarming, since this has been an active, closely monitored volcanic system for 2 decades already. What stands out is that the record for the strongest single earthquake keeps being broken again and again at a pace that keeps compressing. A magnitude 4. 6 event held the record as the strongest in 40 years back in 2025. Just over a year later, a magnitude 4. 7 event took that title away. When the ceiling on the largest observed event keeps rising and the interval between new records keeps shrinking, that is precisely the kind of signature that catches the attention of researchers studying complex geological systems, because it suggests the underlying process driving the seismicity is not simply continuing at a steady rate. It is genuinely intensifying. It also helps to understand what daily life inside this kind of unrest actually looks like for the people living through it, because a single dramatic earthquake headline tends to flatten what is really an ongoing, grinding experience stretched across years. Residents in Pozzuoli have described a kind of learned vigilance that has become part of everyday routine, checking INGV, public seismic bulletins, the way people elsewhere might check a weather app, keeping emergency documents and a change of clothes near the door, and instinctively pausing conversations mid-sentence when a low rumble passes beneath a building. Local schools in the most affected districts have run repeated structural inspections between semesters, and several have had to relocate classes temporarily, while engineers assessed whether cracked walls and stressed foundations remained safe for continued use. Small business owners along the Pozzuoli waterfront have spoken publicly about the strain of watching tourism dip every time a swarm makes international headlines, even though the overwhelming majority of visitors experienced nothing more than a brief news alert on their phone. None of this rises to the level of a full-scale humanitarian crisis, and it is important not to overstate it, but it is a genuinely different way of living than most people experience, an entire metropolitan region calibrating its daily rhythms around a geological process that nobody can fully predict month to month for going on 21 years now. This is exactly where a study published earlier this year enters the picture, and it is worth walking through carefully because it represents one of the more rigorous, data-driven attempts to actually quantify what this acceleration means. Researchers led by a scientist named Zaccagnino analyzed the combined pattern of ground deformation data and earthquake statistics gathered across the entire unrest period, looking specifically at how the rate of change itself has been behaving over time. What they found was not simply that uplift and seismicity have been increasing, but that the pace of increase has itself been increasing, a mathematical signature researchers describe as accelerating acceleration. In plain terms, imagine a car that is not just speeding up, but pressing harder on the accelerator with every passing mile, so that the rate at which it gains speed keeps climbing rather than staying constant. That is the behavior the data is showing beneath Campi Flegrei. And crucially, the researchers describe this as a self-sustaining process, meaning the mechanism feeding the acceleration is not something external pushing on the system from outside, it is something internal to the system itself, reinforcing its own momentum. According to the study, if this self-sustaining trend continues along its current trajectory, the system is likely to reach some kind of breaking point, a critical mechanical threshold, somewhere in the window between 2030 and 2034. It is essential to be precise about what that actually means, because this is exactly the point where casual coverage of stories like this tends to slide into unearned panic. Reaching a critical mechanical threshold does not automatically mean a major eruption. What the researchers are describing is the point at which the accumulated stress and fracturing in the brittle crust above the magma and hydrothermal systems can no longer simply continue accommodating the pressure the way it has been. Something has to give in the researchers' own phrasing. But what exactly gives could take multiple different forms. It could mean an eruption, potentially a small, localized one, rather than anything approaching the scale of the caldera-forming events in the deep geological past. It could instead mean what scientists describe as a regime change, a shift in how the system behaves without magma actually reaching the surface at all, expressed instead through new fracture networks opening in the crust, a surge in fumarole activity at existing vents like solfatara, or even localized ground failure and subsidence in specific spots. The honest scientific position, stated directly by the researchers themselves, is that nobody can say with certainty which of these outcomes is coming. What the data supports is a genuine, quantifiable acceleration, trending towards some kind of transition within the next decade, not a confirmed countdown to a specific catastrophic event on a specific date. To understand why any of this is happening, you have to understand what is actually moving underground. This is where the phrase magmatic fluids becomes genuinely important rather than just a piece of scientific jargon. Deep beneath Campi Flegrei, at a depth of roughly 7 to 8 kilometers, sits the main magma reservoir feeding this entire system. That is not the part actively driving the uplift and earthquakes happening right now. Sitting above it, at a shallower depth of around 3 kilometers, is a separate hydrothermal reservoir, essentially a zone of superheated water and steam trapped within the porous, fractured rock of the upper crust. The current unrest is being driven by the transfer of fluids and gases from that deep magma body up into the shallower hydrothermal system, a process scientists describe almost like a sponge slowly filling. As magmatic gas, dominated by carbon dioxide, seeps upward into the gaps and pore spaces within roughly 3 kilometers of crust, it behaves the way any gas does when it is forced into a confined, already pressurized space. It raises the internal pressure of the entire system. That rising pressure is what physically pushes the ground upward, and it is also what fractures the brittle rock above it, generating the earthquakes that keep waking up residents in Pozzuoli in the middle of the night. There is an important scientific nuance here that researchers have specifically worked to clarify in more recent studies, because it complicates the simple narrative of magma rising toward the surface. Work published in 2023 revealed that the hydrothermal system itself is undergoing a chemical process called decarbonation, where hot, reactive fluids interact with calcite, a carbonate-rich mineral present in the surrounding rock, releasing additional carbon dioxide as a byproduct of that chemical reaction. The research team estimated that this non-magmatic source, meaning carbon dioxide generated by chemistry, happening in the rock itself rather than gas rising directly from magma, contributes somewhere between 20 and 40% of the total carbon dioxide being measured at the surface. That finding genuinely changed how scientists interpret gas readings coming out of the ground at Campi Flegrei. A spike in carbon dioxide emissions does not automatically mean fresh magma is surging upward toward the surface. Sometimes it means the hydrothermal system is simply getting hotter and more pressurized through this chemical process, which remains genuinely hazardous since a pressurized hydrothermal system is exactly what triggers the kind of shallow earthquake swarms that have been damaging buildings and terrifying residents for years now. But it is a mechanistically different kind of hazard than magma physically approaching the surface. This distinction matters enormously for anyone trying to understand not just whether Campi Flegrei is dangerous, which it clearly is, but specifically what kind of danger it currently represents. That distinction has also opened up an entirely new avenue for how scientists and civil engineers are thinking about managing the risk here. And it is worth pausing on because it represents a genuine shift in mindset away from purely reactive monitoring. For decades, the approach to a restless volcano like this one has essentially been to watch and warn, tracking gas emissions, mapping ground motion, logging every earthquake, and maintaining evacuation plans ready to activate if conditions deteriorate sharply. That foundational work remains absolutely essential and has not gone anywhere. But if a meaningful share of the pressure building in the shallow system is coming from groundwater interacting with hot rock rather than purely from fresh magmatic gas, then there is at least a partial engineering angle available that simply would not exist if magma alone were the driver. Researchers have begun discussing possibilities like clearing centuries-old drainage canals that have become clogged over time, better managing surface water runoff so it does not feed directly into the hydrothermal system, and monitoring groundwater levels. With the same seriousness, a cardiologist tracks a patient's blood pressure, watching for the specific fluctuations that tend to precede a spike in pressure-related seismicity. To be absolutely clear, none of this represents any kind of plan to switch off a genuine magmatic eruption. if deep melt were to actually intrude toward the surface, nothing on that scale of geological force is within human engineering capability, and no scientist studying this volcano would suggest otherwise. What it does represent is a targeted effort to reduce the frequency and severity of the fluid pressure crises, the swarms of shallow, damaging earthquakes that have already cracked buildings, buckled streets, and forced periodic dredging of the harbor in Pozzuoli simply to keep pace with a seafloor that keeps rising beneath it. It is worth being honest here about the sheer scale of disruption this uplift has already caused, separate from any question of whether a larger eruption eventually occurs. Streets in Pozzuoli have visibly cracked and buckled under the strain of ground that keeps rising. Buildings across the red zone, the officially designated highest risk area closest to the center of deformation, have needed structural inspections, and in a growing number of cases have been declared unfit for continued use, displacing residents from homes their families may have lived in for generations. Italy's deputy prime minister addressed this directly after the July 31st earthquake, describing close coordination with the prefect of Naples and committing government resources to assisting displaced residents while working toward what he described as a lasting solution for the redevelopment and safety of buildings affected across the wider Campi Flegrei area. That is not the language of a government treating this as a distant hypothetical risk. It is the language of a government actively managing an ongoing, worsening crisis affecting real neighborhoods and real families in the present tense. So how worried should you actually be if you live there, or if you are planning to visit Naples, which remains one of the most visited destinations in southern Italy specifically because of the volcanic history surrounding it? This is the point in any story like this where balance matters more than anywhere else, and it is worth taking seriously rather than rushing past. The seismic events being recorded at Campi Flegrei right now are, in the overwhelming majority of cases, small, magnitude 1 to 3 on the scale, the kind of tremor that might rattle a window or wake a light sleeper but causes no structural damage whatsoever. The magnitude 4 plus events, like the ones in May and July of this year, remain comparatively rare, even though their frequency has clearly been increasing. Ground uplift, while accelerating in cumulative terms, is still measured in millimeters per month on a day-to-day basis, roughly 10 millimeters a month as of earlier this year, a pace that gives residents, engineers, and civil protection authorities meaningful time to observe, adapt, and respond, rather than facing a sudden, unannounced surprise. Italy's civil protection authorities maintain detailed, actively rehearsed evacuation plans, specifically for the designated red zone closest to the caldera's center. And INGV runs one of the densest geophysical monitoring networks anywhere on the planet, with instruments continuously tracking ground deformation, seismicity, gas chemistry, and temperature across dozens of stations scattered throughout the caldera. Millions of people continue to live, work, and travel through this region every single day, and the honest consensus among the scientists actually studying the system, the ones with direct access to the data, rather than the ones simply reacting to a scary headline, is that the risk here is real and worth genuine attention, but it is not the kind of imminent, unpredictable threat that should make anyone believe a catastrophic eruption could occur without any warning at all. That said, it would be equally dishonest to pretend the trajectory of the data is anything other than concerning, and this is precisely why the story deserves real attention right now rather than being filed away as background noise. A self-sustaining acceleration, by its very mathematical nature, does not resolve itself quietly. Systems that behave this way tend to continue along their trajectory until something structurally changes. Either the underlying process driving the acceleration weakens or reverses on its own, which has genuinely happened before in this caldera's long unrest history, with brief pauses and even periods of subsidence interrupting the broader uplift trend at various points since 2005. Or the system reaches the kind of mechanical threshold the researchers are describing, where the accumulated stress in the crust forces some kind of release. Nobody, including the scientists with the best access to the most detailed data, can currently tell you with confidence which of those two paths this specific episode of unrest is going to take. What they can tell you, with a level of confidence built on 20 years of continuous, rigorously collected data, is that the acceleration itself is real, it is measurable, and it has been consistent enough across multiple independent lines of evidence. Ground deformation data collected by satellite and ground-based instruments, seismic records logged by one of the densest monitoring networks in the world, and gas chemistry sampled directly from fumaroles like Solfatara, that it cannot simply be dismissed as noise or normal year-to-year fluctuation. If you are wondering why this particular volcano, rather than the more famous and visually dramatic Vesuvius sitting on the opposite side of Naples, tends to worry volcanologists more when they talk candidly about the region's long-term risk, the answer comes down to a few specific factors working together. Campi Flegrei's eruptive history includes events dramatically larger than anything Vesuvius has produced in recorded human history, including the Ignimbrite eruption 39,000 years ago, An event so vast it deposited ash across a significant portion of the surrounding region and is thought to have had measurable effects on the broader climate at the time. The caldera's behavior is also fundamentally less predictable than a classic cone volcano like Vesuvius, precisely because bradyseism means the ground can rise for years, occasionally pause or even reverse, and then resume rising again, without following the kind of clean, escalating pattern that gives scientists more confidence in forecasting a cone volcano's approach toward eruption. And perhaps most importantly, from a pure risk standpoint, the population living directly within the caldera's boundary and across the immediately surrounding metropolitan area is larger and more densely concentrated than almost anywhere else on the planet sitting this close to active volcanic unrest, meaning even a moderate escalation in activity carries consequences for an enormous number of people simply due to sheer population density layered directly on top of the hazard zone. It is also worth understanding what the earlier, deeper research into the system's long-term magmatic history actually suggests about where Campi Flegrei sits in its broader multi-thousand-year cycle, because the current unrest did not appear out of nowhere in 2005. It is the latest chapter in a much longer story. Studies analyzing the volcano's magmatic evolution over the centuries since its last confirmed eruption, a relatively small event in 1538 that formed a cone now known as Monte Nuovo, suggest the magma reservoir feeding the system has been slowly rebuilding and accumulating since that quiescent period began. Researchers describe this as the beginning of a new caldera cycle, language that specifically implies the system is in a long-term buildup phase rather than a short-term, isolated fluctuation. That framing matters because it reshapes the timescale on which this story should be understood. This is not simply a volcano that suddenly became unstable in the last 20 years for no discernible reason. It is a system that appears to have entered a genuine multi-century accumulation phase, of which the current acceleration in uplift and seismicity represents the most recent, most measurable, and most rapidly intensifying stretch. There's also a wider comparison worth drawing here because Campi Flegrei does not exist in a vacuum, and understanding how it stacks up against other closely watched volcanic systems around the world helps put the current acceleration in proper context. Iceland's volcanic systems, for instance, have produced a string of relatively frequent, well-forecast eruptions in recent years, largely because the magma pathways there tend to be shallower and more direct, giving instruments a clearer, faster read on when material is actually approaching the surface. Yellowstone, by contrast, sits under such an enormous and deeply buried magma system that its current unrest expresses itself almost entirely through shallow hydrothermal activity, geysers, mudpots, and occasional small explosions, without any credible near-term signal of a caldera-scale eruption. Campi Flegrei sits in an unusual middle ground between those two extremes, a shallow hydrothermal system behaving in ways that are genuinely dangerous on their own, layered directly on top of a deeper magmatic reservoir that appears to be in a long, slow rebuilding phase spanning centuries rather than years. That layered complexity is exactly why scientists studying this caldera have to draw on so many different types of instruments simultaneously: seismometers, GPS and satellite-based ground deformation sensors, gas chromatography equipment sampling fumarole emissions, and thermal monitoring of the shallow reservoir, because no single measurement on its own tells the full story of what is happening at different depths beneath the surface. It is also why a genuinely conclusive answer about the coming decade remains out of reach even for the best resourced monitoring network in the world, since disentangling a magmatic signal from a purely hydrothermal one at this specific caldera has proven to be one of the harder technical challenges in modern volcanology. Given everything the data currently shows, what should someone actually do with this information, whether they live in the shadow of this caldera or are simply watching this story unfold from somewhere else entirely? If you live in or regularly travel through the Naples metropolitan area, the most genuinely useful step is understanding whether your home, workplace, or the neighborhoods you frequent fall within Italy's officially designated red zone, the area closest to the center of deformation, where civil protection evacuation planning is most detailed and most actively rehearsed, and familiarizing yourself with the specific evacuation routes and procedures that already exist for your area, rather than assuming you would simply figure it out if the moment ever came. Pay attention to official updates from INGV and Italy's Civil Protection Department specifically, rather than relying on secondhand social media summaries, since this is precisely the kind of evolving scientific story where nuance between an earthquake swarm and an actual escalation toward eruption gets lost extremely easily in translation. If you are planning travel to the region, know that the overwhelming consensus from the scientists and civil authorities actively managing the system is that Naples and the Campi Flegrei area remain safe to visit under current conditions, precisely because the monitoring network in place here is dense enough and the historical bradyseismic pattern well studied enough that a sudden, unannounced, catastrophic escalation without any preceding signal would run against everything the data has shown across 2 full decades of continuous observation. And if you are watching this simply because the science itself is fascinating, which it genuinely is, the single most useful thing to take away is the distinction this story keeps circling back to: the difference between an accelerating, self-sustaining trend and a confirmed, dated prediction of catastrophe. The research pointing toward a possible critical transition between 2030 and 2034 is a serious, peer-reviewed, data-grounded piece of scientific work, and it deserves to be taken seriously precisely because it is careful about what it does and does not claim. It does not say Campi Flegrei will erupt within that window. It says the current mathematical trajectory of ground deformation and seismicity, if it continues unchanged, points towards some kind of mechanical transition within that time frame, and that the nature of that transition, whether it is an eruption, a new pattern of fracturing, or simply a new, more intense phase of the same hydrothermal unrest that has been building since 2005, remains genuinely uncertain. That kind of honest uncertainty is not a weakness in the science. It is exactly what responsible science looks like when it is being applied to an extraordinarily complex natural system that has never behaved in a simple, linear way across its entire recorded history. What happens next depends on data that has not been collected yet, on trends that have not finished playing out, and on a physical system operating on a timescale that dwarfs any single news cycle. Scientists at INGV will keep watching every fresh swarm of earthquakes, every fresh millimeter of uplift, every fresh reading from the gas sensors positioned around Solfatara and the surrounding fumaroles, because each new data point either reinforces the accelerating trend the 2026 study identified or offers the first hint that the system is beginning to settle, the way it has briefly done at certain points earlier in this 2-decade-long episode of unrest. For now, the honest picture is this: the ground beneath one of Europe's most densely populated volcanic regions has risen more than 1.5 meters since 2005. The pace of that rise has been increasing rather than leveling off. The earthquakes accompanying it keep setting new records for strength roughly once a year, and the scientists closest to the data are describing a self-sustaining process that could reach some kind of breaking point within the next decade, without yet being able to say exactly what that breaking point will look like when it arrives. If this breakdown helped you actually understand the real science behind what is happening under Naples, rather than just the scary headlines, hit like so it reaches more people who are trying to understand this responsibly. Subscribe if you want to keep tracking this story as new data comes in from INGV over the coming months. And drop a comment letting me know whether you have ever felt one of these tremors yourself or have family in the region, because those first-hand accounts genuinely shape how we cover the next update. We will keep watching this one closely, because right now this is one of the most carefully monitored, scientifically significant volcanic systems on the entire planet, and the next chapter of this story is quite literally still being written beneath the streets of Pozzuoli. Thanks for sticking with this one all the way through, and we will see you in the next video.